Hello students. In this video we are going to learn about completeness property, which is the last part of our unit on real numbers. So we are going to learn on upper and lower bound, and then supremum and infimum, while open and closed set will be given in the next meeting. So what is it about? So as its name, completeness property of real numbers, it will show us the characteristics of real numbers. If we put real numbers on a line number or a number line, then you can see that it's going to be very complete. Like there's no gap between between real numbers. Like you cannot really have a blank space between each number. So that's simply what it means by completeness in real numbers. But in real analysis, we are going to approach that in a more formal way, which is by learning about upper and lower bound and also supremum and infimum of real numbers. So let's start. So upper and lower bound, as its name again, upper and lower bound. So bound is like a limit, or you can say it's a boundary, while in real numbers it has an upper and lower bound. So upper bounds mean it's a boundary in the upper level or the upper value of real numbers, while lower bound means it's a boundary in the lower value of real numbers. Formally, the definition of upper and lower bound is given like this. So let S be a non-empty set of real numbers. So let's say I have a set of real numbers and I name that as S. So S is a non-empty subset of real number. It's non-empty. That means there's an element there. So the set S is said to be bounded above. So bounded above if there exists a number U, element real number, such that S less than or greater than U for all S element S. So if I have S element S, so I have a set S, capital S, and there's an element of S is named with S, the small s. If S element S here is less than or equal to U, that means this U is going to be the upper bound. Okay. Or if you can see here in the picture below here, so the one that I shade red here is is a set S. So in this set we have elements which we call that as S. Let's say I have S here. The element is, so the elements of S is S small s. So if I have, for example, here I have U. So if your S here, so let's say I have U over there. Say I have, let's say I have U over here. So that means U, because S is here, U is greater than or equal to S. Right? So U is the upper bound. upper bound. So u becomes the boundary in the upper value of s, or you can say in the numbered line, like it's the right boundary there. So u upper bound is any value, it doesn't have to be the element of s, but u can be any real numbers that has a value of greater than or equal to s, which is s is the element of s. So if you, for example, let's say I have something like this. Let's say I have, this is 1 and this is 3 and this is s. So if I have, for example, a value here which is, let's say, 4. So here 4 is the upper bound of s, right? Why? Because 4 is greater than or equal to all element of s, which is all element of s is from 1 to 3, right? Let's say I'm going to choose, let's say I'm choosing 3 itself as the element. So 3 is also the upper bound. Again, because 3 is greater than or equal to all element of s. So that's upper bound. What about lower bound? The set S is said to be bounded below. So bounded below if there exists a number w, element real number, such that w is less than or equal to s for all s element s. So in this case, this is the lower bound. So if you have a certain value, a certain number, real number, and that real number is less than or equal to all s element of s, that means that value is the lower bound. It's my example. Let's say we go back to our example, the red numbered line here. Let's say I'm putting here 1. So 1 is the lower bound. Why? Because 1 is always less than or equal to all element of s. Or I want to put another smaller value, like let's say -1. -1 is also the lower bound. So it is possible for a set to have lots of lower bounds and lots of upper bounds. That's very possible, because the definition of upper bound and lower bound is any value, real numbers, any real numbers that has, for a lower bound, that has less than or equal than the element of s. If it is upper bound, the real number that is greater than or equal to all value of s. Okay. So if a set has upper bound, that means that set is bounded above. If the set has lower bound, that set is bounded below. If the set is bounded, both bounded below and up, above and below, that means the set is called bounded. Just bounded. So if it is bounded, that means it is bounded below and above, both. And if it is not unbounded, if it is unbounded, that means it is not bounded. So that it has no upper bound and has no lower bound. Okay. Now let's try to look at an example. So here you go. Determine whether S is a set and a set of x element real number which x is less than or less than 2. So we are asked to determine whether it is bounded or not. So what we need to figure out is, does it have upper bound and does it have lower bound, right? If it has both, that means this set is bounded. But if it is not, then it's not bounded. So let's understand the set first. So the set say, so our set will be, let's say this is 2 and there's a value over there because x less than 2. So our set will be here, right? Continuously. The element of s will be along this pink shade there, any value there, but 2 is not included. As you see, there's x less than 2, so 2 is not included. 2 is not the element of s. Okay? So when you look at the number line here, I believe you will notice that there's an upper bound, but there's no lower bound. So now let's look at this part. So you see here, so any value, any real number in the green area there will be the upper bound, right? Because no matter what value or what real number that you take from this green part, you will know that the value of that green number will be always greater than the element of s. So let me put here it's s, yeah. So you know that for all, let me write. So for all x element s, you know that x is less than 2. That means that 2 and other numbers greater than 2, which is here I'm writing the value of numbers in the green part there, right? 2 and other numbers greater than 2, because 2 is not included in s, right? Are the upper bounds. See, this set has lots of upper bounds because all values greater than the element of s will be the upper bounds. So I can say like u less greater than or equal to 2. U is the upper bound of s, right? So s is bounded above because it has upper bound. But now let's see the lower bound. So to find lower bound, we need to have a value w, let's say a value w that is less than or equal to s, element s. This is what we need. But in this case, we know that there is no such number, right? There's no such value that is less than or equal to all s element s. So you see that no matter what value that we pick, let's say I'm picking a value here, the red dot there, I'm going to always find another, let's say another value of s over here that is less than that red value. So no matter what small we pick a real number, there is always be an element of s that is smaller. So we cannot find the lower bound of this set. That means we don't have lower bound for this set. So there is no lower bound of s because there is no. So let me write it. There's no w such that, see that this is the definition of lower bound, w such that w is less than or equal to s for all s element s. Okay. Oh, I'm going to use x here so that it's consistent with what we did in the upper bound. Sorry. For all x element s. Right? So because it has no lower bound, so it is not bounded below, right? So it is not bounded. Okay. Okay, so and I want you to try to determine whether this set is bounded or not. So these will be put in your exercise. So after the video, please see that you will find this exercise in number 1 as your exercise. And if you want to do your exercise first, you can pause this video and work on the exercise before continuing to the next part. The next part, we are going to learn about supremum and infimum. Okay, now we go to supremum and infimum. So this might be new for all of us. Supremum and infimum are new terms for us to learn. So let's learn the definition of both. Let S be a non-empty subset of real numbers. So if S is the first part that we're going to learn. So if S is bounded above, so if the set is bounded above, then a number u is said to be a supremum. So a number u is said to be a supremum, or supremum is also called a least upper bound. Least upper bound. That means it's the smallest upper bound. If it satisfies the conditions, there are two conditions. The first one, u is an upper bound of s. So u should be the upper bound first. Then the second, so if v is any upper bound of s, then u is less than or equal to v. So these two statements mainly said that, so a supremum first should be an upper bound first. So supremum should be an upper bound. We know that a set can have more than one upper bound, right? So a supremum should be one of them first. Should be one of the upper bound first. And the second, after we know that u is an upper bound, u is a supremum if phi is any upper bound of s, then u is the smallest, is smaller or equal to v, which phi is any upper bound. So that means supremum should be the smallest upper bound. Okay. So the idea of supremum or least upper bound, as its name, yeah, least upper bound. So supremum is an upper bound that has the smallest value among all upper bounds. Okay. If I show you the picture, so let's look at the picture here. So if S is the set, this red part is the set. Let's say I'm going to put it like this. So here is the set, and we have this red part, red shade of there is all upper bounds of S. Because we know all values there will be greater than or equal to S. Among those all upper bounds, there must be one smallest value, right? So that smallest value here is the supremum of S. See, it's the smallest upper bound. The question is, should supremum of S is the element of S? The answer is no. So supremum can be the element of the set and can be not the element of the set. So it doesn't matter whether the supremum is inside the set or not. But the most important thing is that the supremum should be the upper bound, and the supremum should be the smallest upper bound of all upper bounds. Okay, so what matters are only those two statements. It doesn't matter whether the supremum is inside or outside the set. Okay. So now let's similar logic also apply for the infimum. So infimum works for the set that is bounded below. So if a set is bounded below, then a number W is said to be an infimum. Infimum is the greatest lower bound. Greatest lower bound. I believe you will notice that infimum should be the greatest among all lower bounds, as we learn that a set can have lots of lower bounds, right? Can have many lower bounds, but infimum is the greatest of all lower bounds. So W is said to be infimum also if it satisfies two conditions. The first one, W should be the lower bound. So infimum should be a lower bound first. Then if it is a lower bound, that means it is an infimum if for any lower bound of S, let's say T is any lower bound, then W will be greater than or equal to T. That means W will be the greatest upper bound. So infimum should be the greatest lower bound. Okay. So the formal writing is that T will be less than or equal to W. Okay. Visually, again, visually, let's say I'm going to choose different color. let's say blue, for example. So you know that this is going to be all lower bounds of S. So many. Let's say it's T. So the lower bound is T. And we know there's a value that is greatest among all T. Let's say infimum. We call that infimum as, we name it W. So by these, you know that T is always less than or equal to W, right? In this case, T is always less than equal to W because T is any upper bound. Sorry, any lower bound, I mean. Right? It's also the same with supremum. Let's say I have U is any upper bound, but supremum as, which is, oh sorry, phi is any upper bound, sorry. So V is any upper bound. Supremum U, see that supremum of U will always be less than or equal to phi. So U will be less than or equal to phi. Phi is any upper bound. Okay. So that's the idea of supremum and infimum. Supremum if is least upper bound. Infimum is greatest lower bound. Both do not have to be in the set, do not have to be the element of S. But as long as it is the greatest lower bound and the smallest or least upper bound, then both are supremum and infimum. Okay. Okay, now let's look at an example. So we are asked to determine the upper bounds, lower bounds, supremum and infimum of the set S. Well, the element of set S is 1 over n and element natural numbers. So we know that we need to understand the set first. So S here, because it is, see that it is 1 over n and element natural. So if we make a list of its elements, we know it's going to be 1, 1 half, 1 third, 1 fourth, and so on with 1 over n, right? So it's an infinite set with lots of elements there. Okay. Now, when we try to understand this, we understand that the value of the element along if we put them in order, we know that one will be like the greatest value, the greatest element or element with the greatest value there, because we know it's a 1, and then half will be less than 1 and 1/3 will be less than half. So it is going to be to get smaller and smaller. So we know that because it's getting smaller and smaller and smaller, we know that there must be a greatest value of all those elements, right? Because it's getting smaller. So another way to see this is if you put that into a Cartesian diagram, and let's say this is an element natural number, and you put that is as the value, let's say it's 1. You know, for n element, for n1 it's going to be 1 over there. For n2 it's going to be half here. For n3 it's going to be like 1/3, it's going to be there. You see that the value of the elements of the set are like getting smaller and smaller, right? So if we look at that, we may know that here, see, like the value will be like upper, in the upper level of that, you know that the element of this set will never greater or more than 1, right? It will never uh, more than 1, while it's also never less than 0, because it's impossible to get the negative value for this, right? So by having this visualization, intuitively we know that this set is bounded. It has upper bound, but it also has lower bound. But the thing is, we need to determine what is that, what is or what are the upper bounds and what are the lower bounds. So the visualization indeed help us. So now let's determine the upper bound first. The upper bounds. So we know that for the upper bound, we know that for all x element s, we know that x will never is always, which is x here is defined by 1 over n, right? So the element of s defined by 1 over n, as the question there, 1 over n. 1 over n will always be less than or equal to 1, right? See, it's always 1 or less than 1, right? For all n element natural. See, I'm just like taking the definition here, the definition of the set. Okay. That means we know that because x will always be less than or equal to 1, that means it means that 1 n other numbers greater than 1 will be the upper bound, right? Will be the upper bound. If you look at again, look at the a graph, like the visualization there, we know that any value here, right, the blue shade there, will be the upper bound, because those value like become the boundary in the upper level. So formally I can write that the upper bound, so the upper bound will be the upper bounds, because we have a lot though. The upper bounds are, let's say I'm going to name the upper bound as phi. So set phi is less than, sorry, greater than or equal to 1 for all phi element real numbers. Okay. That's the upper bound. Now the lower bound. So for the lower bound, we know that the lower bound will never reach. See here that below these, the set will never reach 0. So we know that for all x element s, we know that x will always, which is x is 1 over n, will always greater than 0. But it never be equal to 0, yeah? Because 1 over something will never be 0. For all n element natural numbers, so we know that 0 will be the lower bound, like one of the lower bound. So it means that 0 is the sorry, 0 is the lower bound, and also, of course, all numbers smaller than 0 is the lower bounds as well. 0 and other numbers smaller than 0 are the lower bound. Okay, so I can write, let's say, the lower bounds. Let's say I'm writing bound t such that t is less than 0. T is element real number. Okay. Right. Now, when we want to find the supremum, so supremum, the notation for supremum is just sub. So the supremum of S will be the least value of the upper bound. So if you look at this, our upper bound is phi greater than or equal to 1. So if we, let me draw the number line for you. Let's say it's a number line. We have our S, the element of the set will be between 0 and 1, right? 1 is included, but 0 is not, right? So this is our set S. And the blue over there, say it's V, it's the upper bound. And the value there, T, I'm going to use different color, maybe green. Okay. See, T is lower bound here, right? To get the supremum in this case, that means we need to find the least upper bound. You know that among the blue here, the least is this one, right? This, see, it's the supremum of S. Why? Because here 1, supremum of S is 1, because 1 is less than or equal to V, right? For all phi element real number. So for all phi, 1 is the least of all. So no matter what upper bound that you choose, 1 will always be smallest or equal to that upper bound. Okay? What about the infimum? For the infimum, it's E and F for the infimum as. So you see that here among the green one is the greatest. What is the greatest? Oh, the greatest is these. This is infimum S. So it's 0. 0, although 0 is not the element of S, but 0 is the infimum of S. This is what I mentioned before, that infimum and supremum do not have to be in the set. So infimum S equals 0. Why? Because 0, C, is greater than or equal to T, and T is element real number. T is the lower bound. Okay. So I think this is a very good example. For the supremum, you know that supremum is inside the set, right? Supremum is is belongs to S, but the infimum is not, and that doesn't matter. It's okay because supremum and infimum do not have to be in the set or do not have to be outside the set. What we consider, what we pay attention is only the value. We don't care whether it is inside or outside the set. Okay. Okay, I think that's all for infimum and supremum. We are going to learn more about the lemma related to supremum and infimum in the next meeting or in the next video. Okay, thank you everyone. If you have any question, you can always ask through the platform that is given to you. Bye bye.